It's a huge honor to be here today, and I really want to tell you about Lean, get you excited about the project. I want to tell you how Lean is transforming mathematics, software verification, and AI. In all these three areas today, we have to do manual review. In software, we do partial testing. And errors in theorems and critical softwares can have a dramatic, massive consequences. Imagine your cryptography doesn't work and important information leaks. Another thing that we want to address is the fear of making mistakes. It really affects progress. I lost count how many times I met engineers, they come to me, we are not going to make this change because we fear introducing a catastrophic bug. We believe, it's our belief, that Lean provides machine-checkable proofs. Machine-checkable proofs can be viewed as certificates. It can be checked by computers. When you check this kind of certificate, you have absolute assurance the proof of your theorem is correct. The property you verified that your code should have really holds. Right? It eliminates guesswork. It provides trust. If every step is formally verified in your theorem or in your software, the amounts of confidence and trust and collaboration, something we learn after. Our initial goal is to ensure there are no bugs in software. But later we learn that it also enables collaboration in a way we haven't seen before. Lean is an open source programming language and proof assistant. The project started a long time ago. It was a research project, was not meant to be a product. When we started the project, the goal was to merge two independent areas, interactive and automated theorem proving. Since the beginning, Lean had machine-checkable proofs. During the project, we learned that this kind of certificate addresses the trust bottleneck. The trust bottleneck between humans. We see mathematicians so far have been working in small groups because they have to trust each other, their capabilities. But now with AI, is also the trust between humans and machines. It opens many new possibilities for collaboration, machine-checkable proofs. Before we go into use cases, I want to show you a small example. This is a picture. This is a visualization of the Lean development environment where people create specifications, they write theorems, definitions. Like any programming language, you have packages that you can import. Here we're importing MathLib, the Lean mathematical library. In Lean, you can have definitions. I have one here defining an odds number. A number is odds if there is a k such that n equals 2 times k plus 1. Right? It's our definition. Now that we have definitions, we can state claims about these definitions. We can make claims, we can state theorems. Here we have a theorem with a name, we're giving a name. In formal systems, you give names to everything in a way to make very precise what you're talking about. The name of the theorem here is 5 is odd. And the statement is 5 is an odd number. And here's the proof. Here we are saying, we're telling Lean the k is 2. 2 times 2 plus 1 is 5. That's the proof. Lean accepted this. If you provide incorrect proof, Lean will put a squiggly line. This is no different from your text editor. When you have a spelling mistake, you get a squiggly line saying there is a mistake here. Lean will point out the mistake to you. Many people view Lean as an interactive game, right? I remember Kevin Buzzard once approached me saying, "Oh, you have written my favorite computer game." He was worried that I would be offended, but I actually thought it was really cool. I mean, when I was a kid, I loved to write computer games. I was so happy to meet a happy user. I mean, but let's see this example. let's see why people see Lean as an interactive game. Here we are going to write a theorem in Lean showing that if n is an odd number, then the square is an odd number too. On the right-hand side of the screen, we have the game board, right? The state of the game. Like in chess, you can have the board, you can visualize the board. Here in Lean, you can visualize the board too. Here, the board is really small, but when you're doing cutting-edge mathematics, the board can be really, really big, right? Having good visualization tools is really important. Let's see, the first move. We're making a move. The moves in Lean are called tactics. Here we're introducing, intro is when you have a hypothesis that n is a natural number. You're introducing, right? And we give names, like there is a k, we're giving the name, it's k1. And we don't give just name to objects, but we also give to hypotheses, like the hypothesis that n equals 2 times k1 plus 1, we are giving a name, we are giving the name E1 to this hypothesis. Then we use the most popular move in this game, it's called the simplifier. Here we are telling the simplifier to apply the hypothesis E1, basically it's going to replace n by 2 times k1 plus 1, and it's also going to unfold the definition of an odd number. And Lean will highlight in the game board which part has changed. You can see in green the part of the game board that was affected by this move. Then we use the use move again, right? It's the standard way of proving existentials. We are giving the witness here. And again, Lean showing the part of the proof that has been, the part of the game board has been affected. And we complete the game with this linear arith tactic. Linear arith stands for linear arithmetic. We'll do things like applying distributivity, associativity, commutativity, fusing constants. It's a power move, but it completes the game here. Lean is not just an interactive game. Many users say that it's an addictive game. I have a quote here from a student. Well, now she's not a student anymore, but a few years ago she was. And she was saying, actually she gave this one an interview for the Quanta magazine when she said she could do it 14 hours a day, never get tired, and having a high the whole day playing this game. Mathlib. The Lean mathematical library is amazing by itself, but it's also amazing because it supports many, many other projects in mathematics, software verification, and so on. And it's collaborative, it's open source, it's available on GitHub. There are more than 500 mathematicians contributed to Mathlib. It has more than 1.7 million lines of theorems, definitions, proofs, right? It appears on the Quanta magazine the first time 5 years ago. And I love one of the quotes from this article, from Heather Macbeth, when she says that investing time now, that somebody in the future will have an amazing experience. It couldn't be more true. At the time, the user base was really small, but yes, Mathlib was the foundation for projects that we never dreamed would happen right at that time. Let's focus on some use cases. I'm going to start with mathematics. I'm going to start with one project that I think was really special because it brought many other mathematicians to the community. Was formalizing perfectoid spaces. This is 2019. Kevin Buzzard, Patrick Massot, and Johan Comelin decided to see, they want to test if Lean you could define complex mathematical objects in Lean. Is this even feasible, right? It was not clear at all at the time this was possible. Then they decided to formalize perfectoid spaces because 1 year before, Peter Scholze got a Fields Medal, and they felt like, well, many people will want to know in extreme detail what a perfectoid spaces are. Let's try to formalize in Lean. And they succeeded, but they learned a lot from this experience. one amazing thing they learned is that by just the fact you have a formal object, now you can math is data. You can visualize these objects in many different ways. You can transform the object, you can process it, you can inspect it in many different ways. For example, this graphical visualization was not human generated. Basically, it's the dependency graph for the perfectoid spaces project. This is a program they wrote, actually was Patrick Massot wrote this program, that because now math is data, you can build automatically a dependency graph. If you go to Math Overflow, you're going to find the question, what are perfectoid spaces? The most voted answer is Peter's answer, but the second most voted is a link to their project, right? And we're talking about math as data. And sometimes we use terms in the Lean community like, oh, when you have a formal version of a theorem, you can zoom in. You can, even if you want, go back to the axioms of mathematics. Let's see what do we mean by that. When you have a proof in Lean, here I selected a random one from the ring theory library in MathLib. And the first thing is that you can click anywhere in your proof, and Lean will reconstruct the game board at that point. And the game board is not static objects. You can hover and get more information. For example, if we hover over M prime, you are going to see this is a submodule of M. And you may think, I don't know what a submodule is. No problem. You can sneak peek on the definition of submodule in Lean. You can jump to the definition and you can keep going. You can see, oh, a submodule extends additive submonoids. What is this? You can click and keep going, and you can keep going back to the axioms of mathematics. For example, with now perfectoid spaces formalized in Lean, it enables anybody that's motivated to fully understand this object. And you cannot just inspect, you can modify the object and see the consequences. What's going to break, what still works. If you find a simpler proof, you can try it on the spot and get immediate feedback. Peter starts paying attention. After they formalize perfectoid spaces, Peter came up with a challenge in 2020. He said, in 2019, he was obsessed by a proof. He claimed that it was the most important result of his career, and he was getting crazy about it. I'm just quoting him. But he finally pinned down a proof on paper, but he was not sure. Nobody was checking his proof because of the complexity, and he had doubts about it. And he posed a challenge. I want to see a formal version of this proof. At the time, Kevin Buzzer has told me, we are going to try. It may take years, right? But we will try. Doesn't matter if you take 3 years to do it. We will try it. To our surprise, again, the power of the community, people working together. Johan Comelin led a team. In a few months, they managed to formalize the crucial intermediate lemma that Chose was unsure about. I think the whole community was surprised by how quickly they had managed to do it. And the result appears on Nature. I think was the first victory for the Lean community. But it didn't stop there. What was even, in my point of view, much more surprising was the fact that they not just verified the proof, they simplified the proof. Without fully understanding the proof. Johan told me that he could see 2 steps ahead. Basically, Lean was serving as a guide. He could see 2 steps ahead and kept going, but he figured out he could simplify. There was an object that he felt like, oh, I can use a much simpler object. Now that I can use Lean to check every step, I'm going to use a much simpler object to prove this theorem, and he succeeded in doing that. I think this was really surprising that a team of many contributors, many of them never met in real life, they are only online, they managed to verify these results that were beyond their understanding of mathematics and simplify the results. I think for me was one of the happiest days, especially when I read this quote from Peter saying that Lean was an assistant, really an assistant, navigating through this thick jungle that proof is. And keeping all the objects in his mind was really hard. I mean, and the same thing happens when you're trying to read his proof. This was only the beginning. There are many other projects, mathematical projects using Lean. Happy to see Alex Kontrovic here today. His project, Prime Number Theory and Beyond, is super exciting. There's another big project, Fermat's theorem, Formalization. Kevin keeps telling me that nobody knows the whole proof. I mean, people know parts of the proof, but nobody understands the whole thing. And now, in a formal version, you'll be able to visualize it, every single detail. Anybody that's motivated will be able to fully understand the proof. What we learned here, right? Sorry, before I have to answer this question that people ask me every single time. I decided to include the slides about it. Can we trust Lean? Lean may have bugs. I mean, you're talking about machine checkable proofs. Yes, Lean has many bugs. It's a huge system, right? As any huge system, it has many bugs, right? And this kind of system is really hard because there's no spec. What's a proof assistant? The spec, the specification keeps changing. Our users come to us every single day asking for changes, modifications. To say a program is correct with respect to specification. If the specification keeps changing every single day, it's hard. I mean, the program will have bugs, but it is huge, but has a very small trusted proof checker. That's the part that you have to trust. It's small, but you may say, okay, it's small. This part, the spec is clear, but it may still have bugs there. Okay, yes, you're right. You may still have bugs, but remember, math is data. You can export your proof and check with external checkers. That checker is implemented in C, C++, Rust, Lean, and so on. You may say, oh, all of them may be buggy. Yes, you can implement your own. The spec is clear for this trusted kernel. You can implement your own checker. You can export the whole math lib and check yourself. Just to give perspective, the Rust checker was written by a lawyer. I mean, he's a really smart lawyer, but he wrote his own checker and can check the whole math lib, his checker. What we learned, I think for me the most important learning here was collaboration. The new level of collaboration. It's not about checking whether your proof is correct or not. It's now the ability to collaborate with people you never met before. The power of the community, having people working together, being able to achieve more. And having an assistant that allows you to go beyond your cognitive abilities. These were, for me, were the main things we did not expect when we started the Lean project. And there is also this one that's from one of the mathematicians in the Lean community. I love this message. He posted in the Lean discussion channel on Zulip. And this is something that happens in software engineering. You refactor your code automatically using tools. But here was great to see it happening for mathematics. Basically, someone made a result more general and was saying, it is amazing that we are going to propagate automatically that. And he said, imagine if someone made a result from a paper 50 years old, and you have to track every single paper that used this paper and update manually. Nobody will do it. But with formal mathematics, you have all the dependencies, math is data, you can do the whole process automatically. Right? I love this message. Software, let's talk a little bit about software. I'm a computer scientist, I have to talk about software, right? Lean is a programming language. You can write code in Lean, and you can verify code you have written in Lean. You can do both simultaneously. And this is powerful because testing can, this quote from Dijkstra, that testing can show the presence of bugs, but not their absence, right? And we experience bug codes all the time. And it would be great to live in a world where critical software does not have bugs. Differential privacy is a mathematical framework that ensures the privacy of individuals is preserved when you're trying to collect data from your users, but you want to respect their privacy and want techniques to add random noise to the data. And differential privacy uses algorithms like a discrete Gaussian sampler. And you have to be really careful there, because if you add too much noise, the data is useless. If you add too little, privacy can be compromised. A friend of mine, Jean-Baptiste Tristan at AWS, he wrote an open source Lean library that does verified differential privacy for many primitives. His implementation is not just verified, it's twice as fast. He managed to do it because he could do aggressive optimizations without fearing the introduction of bugs. He could do things that other developers were scared to do because he had Lean as a guide. In Tensor, this project would not exist without MathLib, right? Tensor, differential privacy, you may feel like software only relies on trivial mathematics, but this is not the case. Differential privacy relies on many mathematical concepts, ranging from Fourier analysis to number theory, topology. It's a non-trivial project. And what did we learn with this project is that you can code without fear. I think this is powerful. You can code with absolute assurance that your optimizations are not breaking your code, you're not introducing a catastrophic bug. There are many other projects about verified compilers, policy languages, cryptographic libraries. You can learn more about them on a blog post I wrote once. There's a link here. These slides will be available online. I have a QR code at the end you can use to access the slide deck. You can also check our repository of packages, Reservoir, where all the Lean packages that are open source are available there. AI. Lean enables AI for mathematics and code, right? AI, large language models are powerful tools. They're getting better every month, but they hallucinate, they make small mistakes. In math, a small mistake can invalidate the whole proof. Imagine trying to verify manually that an AI-generated proof of Fermat's theorem is correct. The informal proof is over 200 pages, right? Who is going to check that? And I remember talking to Terence Tao. He made an excellent point that a human mathematician, they are really trying to do their best, right? They are trying to get it right. While the AI, sometimes you have the feeling, is trying to please you, and it can try to deceive you by trying to address your question, to make you happy. It will try to mislead you in believing something that's not true. And sometimes the mistakes are really subtle. The amount of time you spend trying to check is far greater. But machine checkable proofs are the antidote for hallucinations, right? We have today AI proof assistants that are ready us to write proofs. Several groups are developing AI that can suggest the next move in this game, that is this interactive game you play with Lean. The same way we can train AI that can play chess, that can play Go, you can train AI that can play this interactive game. This interactive game is much, much harder. Some people, especially people that do not have advanced math classes, they think math is like chess. It's the same difficulty level. It's completely different dimension, right? Math, you can say, is a bounded game. The number of moves you can take is unbounded. But I listed a few projects that I really like it for Lean. Lean Dojo. I'm super happy that Caillou is here today. He's the leader of the Lean Dojo project, an open source project from Caltech. One thing that's really memorable there is that everything is open. The model, the data sets, the code. Now, if you have a PhD student that wants to work in this area, they can start from something that already works. They can try to make it better, but everything is open source. I'm a strong believer of open source code. And it's amazing to have everything open. This is how we make progress in science. OpenAI and Meta AI have also developed AI assistants for Lean. And before I keep talking about these other projects, I want to show how it looks like. We have the same, here the Lean development environments again, and you can ask Lean now, ask the AI, give me a suggestion. And now on the right-hand side, you don't have just the board game, but also suggestions. And the AI, you can use Lean to check if the suggestion is correct or not. And it will tell you, look, I finished the game for you. Here's the move, right? And AI for constructing proofs will keep getting better and better. And they're already doing fantastic things, like AlphaProof from Google DeepMind. AlphaProof was built on top of Lean, and basically they managed to get the silver medal level at the International Mathematical Olympiad. The IMO is a high school level competition, but this is extremely hard, even for professional mathematicians. Many of my colleagues thought it was impossible to get an AI that could get us at this level. And they almost got the gold level, at the gold level, was almost there. And probably next year is going to be gold. They almost got the gold medal level. I remember people saying, no way AI can do that. And they did, it happened, right? And it's just the beginning. But the main important thing here is that they have a certificate that the solutions found by the AI are correct. Auto-formalization is another area where it's having a big impact in systems like Lean. The main point of auto-formalization is to convert natural language into formal one. And this is powerful because, like learning a new language, natural language, it's much easier to learn how to read than to write. I met users that they learn how to read Lean in one day. Right? Some take 1 week, some take longer, but you can learn to read it's way faster to learn to read. And now imagine you can write natural language and convert to formal language. You have the AI doing that for you. And you just double check, oh yeah, that's what I want. And now you can start proving things about your statement. Lean8 is one of these auto-formalization tools, but now all major large language models are doing a great job at auto-formalization, and they are going to keep getting better and better. What did we learn here, right? Machine checkable proofs enable AI that does not hallucinate. Large language models enable auto-formalization. They are also getting really good at explaining Lean codes. You can get any proof from MathLib, put on one of the major large language models, and they will explain you what that means. And you can even interact, ask, oh, explain me step by step what this move does. It will explain to you in natural language. And in the era of large language models, machine checkable proofs ensure that we can trust the results. Right? Before we wrap up, there are a few things I want to tell you. One is how we manage. I mean, Lean started as a research project, right? For many years, I was the only person working on the project. Then Sebastian Ulrich and I started building Lean, but it was just the two of us. One key ingredient that made Lean possible is decentralized collaboration. Machine checkable proofs helped, right? You don't need to trust us to use our proofs. You don't need to trust our automation. You can code without fear. I try to promote this idea during this talk. But another ingredient that's really important is that Lean is extensible. Users can extend Lean using Lean itself. Actually, Lean is implemented in Lean. You can make it your own, right? And the mathematicians do that all the time. They do not ask permission to change how notation looks like in Lean. They do not have to ask us to add a new move to the game. They can add the move themselves. It turns out the linear riff move was implemented by mathematicians, by the MathLib community, in the MathLib community. They implement themselves this move. They did not come to the Lean developers and ask them, oh, I need a move that does linear arithmetic for me. No, they implemented it themselves. And this is powerful. They wrote Lean code. They did not have to learn a new programming language. They knew Lean already. They wrote in Lean this new move to the game. And Lean is also popular with AI researchers because you can introspect on its internal data. You can use Lean, you can write Lean code to traverse the Lean proofs as data. You can use that to extract training data for training AI. You can extract this data for writing your own checker. You can extract data to build visualizations, even proof animations. You can create videos. There is a package for Lean that enables you to create an animation for any proof constructed using Lean. If you search YouTube for Lean proof animation, you're going to see many examples. The Lean Flow. Now let's talk a little bit about the future. Lean Flow is a focused research organization. It's a non-profit dedicated to Lean's development. It started in August 2023, now has 19 members, and the mission is to enhance critical areas like scalability. Scalability is super important. MathLib is 1.7 million lines. We want to give feedback as quickly as possible to the users. You want to know if when someone makes a change to the library, what's broke. It's really important, scalability. And the complexity of the mathematical objects that the community is attacking keeps increasing all the time. Usability is also super important. We want Lean to be usable, approachable to even high schoolers. You want people in high school being able to use proof assistants, and you need to improve usability. You have to make the system easier to use. Proof automation, we always need new moves to make the system more convenient. A software system usually is successful if it is convenient to use. Systems that are not convenient to use usually is really where they become successful. So making things convenient is important. Another mission for the Lean Flow is to reach self-sustainability in 2028 and move into a foundation. And we're really, really grateful for the philanthropic support of the Simons Foundation, Alfred Sloan Foundation, Richard Merkin, and Founders Pledge. It would be impossible to keep the project going. It's not a research project anymore. We have to serve the mathematical community. There are also physicists building a A library like MathLib for physics, high energy physics. There are users building libraries for computer science and so on. For chemistry, we want to serve our users. And it's not like we're doing a research project anymore, trying to combine two different areas. Now, our job is to serve these communities. And you need engineers that are working full-time on the projects. The Focus Research Organization, this concept came from convergent research. It's inspired by projects like the James Webb Telescope and CERN. Projects that are too big for academia and they are not profitable enough. It's not clear how to make money with them. Then VCs will not put money on these projects. Industrial is also not good, it's not profitable for industry. How to support this kind of projects? That's why convergent research created the flow concept. Since we started Lean Flow, we had 16 releases, more than 3,400 pull requests. A pull request is a contribution to Lean's open source. You have to submit your contribution to the repository that's public. There were more than 3,000 ones. I have here the numbers for the latest release that contains more than 168 new features, more than 50 bug fixes, documentation improvements, and so on. All this information is available online. You can go to GitHub, you can see every single release for Lean and see which features have been added in each one of them. The Lean project has been featured in multiple venues like the New York Times, Quanta Magazine, Scientific American, and so on, and we are really grateful for their support. I want to show a little bit about the growth of the project and the acceleration after we launched the Lean Flow. Here's the number of packages, projects on GitHub. Now today, you see there are more than 4,000 projects. We didn't expect this kind of growth, but we are really grateful and really happy to see it. The number of installations of Lean. We have data starting from 2024, and there are more than 40,000 installations since the beginning of 2024. And we are really confident we are going to get to 1 million and beyond. A common question I get is, how can I contribute? There are many different ways. You can contribute by helping to build MathLib. There are areas of mathematics that need to be covered in MathLib. For example, partial differential equations. We have users for that. Having people contributing to this part of the library would be fantastic. You can engage with the community on the Lean Zulip channel. You're going to find many mathematicians there. You find beginners, AI researchers, software verification people, everybody there talking about Lean and telling others about their experience, and they will answer your questions in a few seconds these days. If you're interested in machine learning kernels, you can contribute to an open source one being done in Lean. If you want to contribute to a very large formalization project, you can help the Fermat's theorem formalization project. You can create your own open source Lean project, your own package, and it will be available on Reservoir, our registry. You can start using Lean today. You can go to live.leanlang.org and you'll be able to use Lean without having any, you don't have to bother to install anything. It will be there with MathLib available to you. You can support Lean with funding, partnerships, or simply advocating the project. Advocacy is so important. Spreading the word, telling others, getting new users. I'm really happy to be here today. Lean is an efficient programming language proof assistant. It's my belief the MathLib community is changing how math is done. They inspire me every single day. It's not just about proving, It's not about making sure the mathematical results are correct. That's not the goal. The goal is getting new insights, going beyond our cognitive abilities, being able to navigate through these thick jungles that we couldn't before. Lean will track the details and enable us to focus on the big ideas, right? Decentralized collaboration enables teams to work together, teams that never met before. Yeah, this is what keeps us going and developing Lean. Thank you very much for your attention. This slide deck is available online. You can get with the QR code. Thank you.
Thanks so much for this wonderful lecture. Thank you. Any questions? Many questions. Oh, yes.
Obviously, Lean is not the first proof system, and people in the past using a variety of other proof systems have experienced like troubles like navigating the proofs, and there's the huge usability aspect of it. So I'm wondering, like, what is the like the secret sauce of like that you have put into like programming language design and also the tool design that make mathematicians find Lean like very usable in some sense?
Great. Great. I can tell my perspective. Of course, it's really hard to compare with other systems. I have tremendous respect for all of them, right? I mean, but a few things I believe. The first thing, we really listen to the math community, right? So our first users, the first one was Jeremy Avigad. He's my friend. Tom Hales was a user at the beginning. They gave valuable feedback, and we really listened to the feedback. Paying attention to your customers, to your users is really important. So I think the first thing. The second thing was making Lean extensible. We didn't have resources, right? Some people think that we had a team of engineers in the beginning. No, there was nobody. It was just me and students helping, right? Being able to make Lean extensible enable the mathematicians to make Lean their own. And everybody that uses MathLib, you see they customize many different things to make Lean feel like how they wanted, right? I think that was important. Another thing that was important was scalability, making sure it scales. The mathematical objects that in MathLib, when you use MathLib, you see the abstraction. You don't see the real object that's inside of the machine because the complexity is so high, it should blind you. And being able to scale to this kind of object was also important for the success of the project.
Yes, please.
Hi, thank you very much. I'm wondering if the Lean system can demonstrate that a purported proof of a claim is actually invalid and point up where it goes wrong, either with respect to one of the premises assuming the conclusion or contradictions in the premises. So
Yes.
can it do that?
Yeah, well, if you provide a formal proof to Lean, there is a mistake, it will tell you where the mistake is. But I believe you are asking is, suppose that I'm making this claim, can you find a counterexample automatically, right? This is an active area of research, right? For right now, only for simple claims, we can make that, you can create counterexample for simple things. But for complex mathematical objects, this is an active area of research to come up with counterexamples for. Yes.
Thank you. I want to address the software verification aspect that you mentioned. So, if you have something very common in a programming language, you have a control structure. Let's say like if. And in some languages allow you basically to break the contract of that control structure by branching into the middle of it by bypassing the evaluation of the condition. So, so in other words, you execute code in the control structure even if the condition is false. Can Lean catch stuff like that? I mean, that kind of verification should actually be part of the programming language. But can Lean catch stuff like that?
Well, the first thing, there are many different ways to answer your question. The first thing, Lean we call is a well-behaved programming language. You cannot write this kind of code in Lean that you jump inside. Lean is mathematical, but suppose that you're trying to verify a program written in a different programming language that allows you to do that. The first thing I say, programming languages that allow you to do that are not a good match for verification, but you still can do it. You're going to suffer more to make the verification, but the first thing you have to do is to give it the semantics precisely, mathematically in Lean of this programming language.
Okay.
After you do that, you can start the verification process and you can do it. But languages that have, I know the programming languages that do things like that, they are convenient, but eventually you pay the price. If you want to reason about, I think this kind of programming language is great for writing disposable codes. Like you want to write a small script that you're going to run once and throw away. This kind of programming language is awesome, but if you're trying to write a critical system, I think it's a bad idea.
So basically you have to debug the language.
Yes.
Question about formalization. I can make a statement in English that is perfectly clear to me. I know what I mean, but different people will have a completely different meaning from my meaning. Can Lean, how does Lean formalize something like this?
Okay, great question. I mean, sometimes you can, I think you let me try to repeat what you are trying to say. Let's see if I understood correctly. I think one concern, and it's a valid concern, is that you may think you stated a specific result, but it's not exactly the result. You're trying to prove something else, and you succeeded proving, but the statement is not the real result you wanted. This is a common question we get. Lean does not help you to check if the statement is really what you want. It doesn't know what you want, or what other people want. But how do we debug a statement in Lean? We debug a statement by proving facts that we know should hold if this statement is what we want. That's how we do it. I mean, for example, if you formalize real numbers in Lean, you're going to start proving many properties about the real numbers and say, okay, yeah, these are the real numbers I wanted. I mean, by proving properties about the objects, we make sure that we formalize what we really wanted. Another thing you can do, now that you have a formal version of your statement, even if you don't prove anything about it, you can go through the dependencies. You can say, oh, what plus means here? What times means here? You can keep asking these questions, and Lean will help you. And you can convince yourself this is the real thing. The same process we had the similar process with Peter Schulze. I mean, for the liquid tensor experiment, he was there asking, I really want to make sure you are formalizing what I want, not what you think I wanted. And it was a process, and he was convinced in the end.
This is a question not just about Lean, but in general about proof formalization. In that, from what I remember, there are various incompleteness proofs going back to Gödel. So basically, if you have a set of axioms that you can do essentially basic arithmetic in, you'll either have contradictory statements or undecidable statements.
Yes.
I mean, is that something that you find problematic in this type of formalization?
No. This kind of thing is never really a problem in practice. I think foundations are important, but I've seen many people thinking that one roadblock for proof assistance is the foundation. Which foundations we are using, this is not really the problem. I compare with computer science. Computer science, you have different foundations. One of them is Turing machines. You can write any program in a Turing machine, but it's super inconvenient. To make proof assistance real, what's important is convenience. You have to make it feasible for people to formalize what they want. These incompleteness theorems, this is great information, but this is not really a roadblock for mathematics. Most mathematics can be done in as fragments of the power that Lean provides, right?
Hi, I'm Ben. I'm one of the 4,000 people who started a Lean project last month. Don't need to clap, it's not finished yet. I like Lean a lot, but I was extremely frustrated with the large language models and their ability to help suggest things for the proof. So my question is, what setup do you use with AI tools and LLMs that you feel makes your productivity so much better when using them?
Okay, great question. I usually use, I don't use the default that most members of the community use. Most members of the community, they tell me Cursor is amazing, Copilot is amazing. I think Alex from Trevish uses Copilot. He's the one that told me he has a great experience with Copilot. I use more like a sandbox. I talk with a large language model. I show Lean codes and start telling what I want to do, what the transformation I want to perform. I use like a soundbox, right? I keep talking and explaining, getting feedback. But if you're using directly, I mean, Cursor, it works great. I hear many good things from the community, and Copilot too.
Hi, I'm not a mathematician, I'm a physicist, but every once in a while I get this urge to, or an idea to try, but always feel like there's a barrier for entry into, and so I look for mathematicians to talk to, but based on your comment that you need help with extending Lean into PDEs and whatever, so it seems like if I come from the outside and I want to use Lean to try things out, I might find that some of the basic objects are not defined, so there hasn't been enough development. Is that how, like basically problems in statistics, in spectral theory, yeah, there's no guarantee that anybody has done any work on this preparatory work, okay.
Yeah, but one thing that, if you want to start something, the best place is to join the Zulip channel, talk with the community. You're going to find people will give you tons of feedback. That's how you should start. That's the first steps. This is what is missing.
Hi. When I first heard about Lean, I was a little surprised based on the original goals of combining automated and interactive theorem proving. That I wasn't more like F-star, combining also based on the author, not combining like Z3 with a dependently typed language or something like that. And I'm guessing it's because of the independent verifiability, like trying to make that possible. But I'm curious, are there any plans to do like a Z3 as a Lean tactic in the future, or is that already being worked on or done or anything?
Yeah, we are working currently on a tactic called grinds that you can view like Z3-like tactic.